Now we're going to plunge into some yet more detailed synaptic physiology and chemistry to give you a feel for how the information mechanisms at higher levels rest on the underlying chemistry. Remember, a synapse is the place where the activity of one neuron affects another neuron, and the weight of the synapse is the size of the effect. When we learn something, ultimately that learning has to be implemented at a detailed level by changes to the way neurons affect each other. In other words, by changes to synaptic weights. This shows one glutamatergic synapse located on its spine on a dendritic branch, and in this case it's quite a long way from the soma of its neuron. Now all action potentials are very similar, but as I mentioned, the effect of an action potential arriving at a glutamatergic synapse depends on the strength of the synapse, and the strength of the synapse changes depending on its pattern of activity, although over time the strength tends to go back to its earlier value unless there's activity at other synapses, such as dopamine synapses, that are often located close to the spine of the changing glutamatergic synapse. Synaptic weight changes depend on the fact that when a neuron produces an output action potential, at the same time it also generates an action potential that backpropagates into the dendritic tree. So if a glutamatergic synapse receives an input action potential, and shortly afterwards the neuron produces an output, so that the backpropagating action potential arrives at the synapse not long after the incoming action potential, the weight of the synapse increases. And the timescales here are of the order of tens of milliseconds. In other words, provided the incoming action potential arrives at the synapse a few milliseconds before the backpropagating action potential, the synaptic weight increases. On the other hand, if the backpropagating action potential arrives before the incoming action potential, the weight of the synapse decreases. And if the time between incoming and backpropagating action potentials is long, the synaptic weight isn't going to be affected. And we can plot the change as a function of the arrival time difference. And again, all this happens within a few tens of milliseconds. The biggest increase occurs if the backpropagating action potential arrives about 3 milliseconds after the incoming spike. The biggest decrease occurs if the backpropagating action potential arrives about 2 milliseconds earlier than the incoming spike. Now, there's an information interpretation of what's going on here. If the input to the synapse occurs just before the neuron produces an output, then the synaptic input probably contributed to creating the neuron output, which indicates that the synapse is relevant to the neuron receptor field detection, and an increase in weight is appropriate. On the other hand, if the input to the synapse occurs after the neuron produces an output, then the synaptic input was irrelevant to creating the output, indicating that this synapse is not very useful and a decrease in weight is appropriate. The increases triggered by this relative timing of incoming and backpropagating action potentials decay with time. They only last about an hour. However, if within that hour there's an incoming action potential at a dopaminergic synapse, the weight change is confirmed for a much longer period by permanent growth of the spine. So now let's shift to an even more detailed level to understand the weight changes in mechanical terms. A glutamatergic synapse is made up of a swelling on the end of a dendritic spine called the postsynaptic part of the synapse, and a swelling on the incoming axon that's called the presynaptic part. Between the presynaptic and postsynaptic parts, there's a narrow gap called the synaptic cleft. On the surface of the postsynaptic part, there's a region that appears darker on stained microscopic views, and it's called the postsynaptic density. And as we'll describe a little later, this postsynaptic density contains chemicals that respond to neurotransmitter released by the presynaptic part. When a presynaptic action potential arrives shortly before a backpropagating postsynaptic action potential, a very short-term effect is an increase in the efficiency of the chemicals in the postsynaptic density, increasing the response of the synapse for a matter of minutes until the increases decay away. A somewhat longer-term effect, lasting about up to an hour, is an increase in the concentration of chemicals in the postsynaptic density, again increasing the response of the synapse. But once again, the higher concentration tends to return to the equilibrium concentration. However, if the dopamine signal is received before the higher concentration has disappeared, an increase in the size of the synapse occurs, locking in a weight increase longer term. A silent synapse is one with structure but no synaptic weight. Such synapses can acquire weight by the same synchronicity mechanism, giving a way for example, a neuron to add a provisional input and only give it weight if it seems relevant.